Now we will discuss on the second part of information theory and entropy. Actually, in the previous part, we emphasized on information theory and we covered information theory not in details but different aspects, and we provided a broad outline of different aspects of information and different categories of information. And in this topic we will emphasize on the entropy. Now entropy, the concept of entropy is closely related with the concept of information, but basically the concept of entropy was originated from the subject physics, rather thermodynamics. Not only physics, it was originated from thermodynamics, which is a common area of physics, astrophysics, and chemistry. Therefore, entropy is a fundamental concept in thermodynamics, information theory, and statistical mechanics. It can be understood in various contexts. Number one, thermodynamic entropy. And let us outline the different contexts. Number one, measure of disorder. Entropy measures the disorder or randomness of a system. Heat transfer. Entropy is related to the amount of heat transferred between systems. Second law of thermodynamics. Entropy always increases over time in a closed system. Next, information theoretic entropy. Now, number four, measure of uncertainty. Entropy measures the uncertainty or randomness of a probability distribution. Number five, data compression. Entropy is used to quantify the compressibility of data. Number six, Shannon entropy, a mathematical formula to calculate the entropy of a probability distribution. Next, statistical mechanical entropy. Number seven, microstates. Entropy is related to the number of possible microstates in a system. Number eight, Boltzmann constant. Entropy is proportional to the logarithm of the number of microstates, from where Boltzmann theory is formulated. And next, Gibbs entropy formula. It is another mathematical formula to calculate the entropy of a system. Next, interpretation of entropy. Number 10, disorder. Entropy can be seen as a measure of disorder or randomness. Number 11, uncertainty. Entropy can be interpreted as a measure of uncertainty or lack of knowledge. And number 12, information. Entropy can be seen as a measure of the amount of information in a system. There are many other implications of entropy. From the context of thermodynamics, entropy is also viewed as a measurement of unavailability of energy of a closed system. That is, entropy measures the energy which is transformed into some unavailable form. That is the point. Let us now highlight the root concept of entropy. Now, that is how the concept of entropy was defined in thermodynamics. Now, in thermodynamics, entropy is a measure of the disorder or randomness of a system. It is a fundamental concept that helps us to understand the direction of spontaneous process such as heat transfer and chemical reactions. Now, second law of thermodynamics, the total entropy of an isolated system always increases over time except in reversible process. Definition: entropy is a thermodynamic property that represents the amount of thermal energy unavailable to do work in a system. And this is the basic concept of entropy. Entropy points out the thermal energy transformed to be unavailable. Actually, this is very interesting. For instance, we know, let us consider the sun. Sun is continuously radiating heat. How? Because the temperature of the sun is larger compared to its surrounding temperature. But as a result of continuous radiation of heat, the surrounding temperatures of the sun is very slowly increasing. Now, one day may come when the system temperature of the sun and the surrounding temperature of the sun becomes more or less equal. And what will happen then? The sun will not be able to radiate energy. And the situation which is known as thermal death, at that time the sun will not function and gradually it will be dead, and it will then, after so many processes, eventually it will be converted into a dead star. There are many names, many forms or phases of dead stars, like white dwarf star is there, neutron star is there, and eventually the black hole. So this is the point. Therefore, entropy is very important phenomena in the context of astrophysics and cosmology also, particularly in the context of black hole physics, the black hole entropy, entropy in the context of dead star, or entropy in the context of neutron star. Those are very significant areas of study. So therefore, this is the point. Entropy points out some energy which is unavailable to do any work in a system. That is the inert energy. Yes, energy is there, but that is not doing any function. Inert energy or sleeping energy. And in this way, the living system gradually transformed into an inert system. That is the point. And another implication is there: the inertness of the system increases the chaos. Therefore, entropy also is a measure of chaos within a system. Chaos, which is the which is defined as a contrasting feature of order. Order means disciplined, and chaos means disorganized or indisciplined. So, this is the basic concept of entropy. Entropy in physical system, it is related with unavailable form of energy. It is related with lack of order and chaos. That is the point. And the entropy of the universe can never decrease. The entropy of the universe is always increasing continuously. Now, the unit of entropy is joules per Kelvin, and the entropy change or delta S, entropy is represented as S, and change in entropy is represented as delta S. Entropy change of a system is the difference between the final and initial entropy values. Now, entropy change or delta S is equal to Q by T, where Q is the amount of heat transferred and T is the temperature at which the heat is transferred. Therefore, entropy change is the ratio between quantity of heat and temperature. On this basis of the definition, the Clausius inequality was defined, which is delta S greater than equal to Q by T, which states that the entropy change of a system is always greater than or equal to the heat transferred divided by the temperature. Next, Gibbs free energy, that is delta G is equal to delta H minus T delta S, which relates the change in Gibbs free energy delta G to the change in enthalpy, that is delta H, and entropy delta S. So this is very important formula. This formula relates entropy and enthalpy with Gibbs free energy. Applications of entropy, let us now point out there are many applications. For instance, at first, heat engines. Entropy is used to calculate the efficiency of heat engines and refrigeration systems. Next, chemical reactions. Entropy changes are used to predict the spontaneity of chemical reactions. And next, thermodynamic cycles. Entropy is used to analyze and optimize thermodynamic cycles such as the Carnot cycle and the Rankine cycle. Let us now point out some important concepts related to entropy. Number one, reversibility. A reversible process is one in which the system and its surroundings can be restored to their initial states. Next, irreversibility. An irreversible process is one in which the system and its surroundings cannot be restored to their initial states. Next, entropy production. Now, entropy production is the rate at which entropy is generated in a system. Next, entropy and chaos. Entropy and chaos are two closely related concepts that describe the behavior of complex systems. While they are distinct, they are often interlinked, and understanding their relationship can provide valuable insights. Entropy measures the amount of disorder or randomness in a system. In thermodynamics, entropy describes the amount of thermal energy unavailable to do work, and in information theory, entropy measures the uncertainty or randomness of a probability distribution. Now, chaos refers to complex, unpredictable behavior in dynamic systems. Chaotic systems are highly sensitive to initial conditions, leading to drastically different outcomes. Chaotic systems are inherently unpredictable, making it challenging to forecast their behavior. Therefore, let us now recall the thermodynamic definition of entropy, which is the ratio between quantity of heat and temperature. Similarly, in the context of information theory, the entropy is defined as the average number of information content per message, that is, amount of information divided by number of message. Therefore, there is an analogy between these two. Here in thermodynamic system, the entropy is the ratio between heat by temperature, and in information theory, entropy is the ratio between quantity of information divided by number of messages. Therefore, amount of heat is replaced by quantity of information, or quantity of heat is replaced by quantity of information divided by temperature. It is an indicator of the state of heat, and here the temperature is replaced by number of messages. Hence, information quantity of heat is replaced by quantity of information. Thus, information per unit message, number of amount of information content per unit message. Hence, information is analogized as equivalent to energy. This is the point actually. This is the point to be noted. Actually, uh, in physics, in thermodynamics, or in physics and astrophysics, what is energy in information science, that is analogized as information. And also we know in physics, information is also defined as the electromagnetic radiation. And yes, electromagnetic radiation also, it is nothing but a form of energy. Therefore, from this analogy, the entropy, the concept of entropy was arrived from physics and astrophysics and chemistry to information science. That is the point. Let us now discuss on, we have discussed the entropy and chaos, where we have seen that entropy and chaos are two closely related concepts that describe the behavior of complex systems. While they are distinct, they are often interlinked, and understanding their relationship can provide valuable insight. Also, chaos is also closely linked with the concept of information. The relationship between information and chaos is complex and multifaceted. Chaos can both facilitate and hinder the flow of information. Chaotic systems can explore a wide range of possibilities, leading to the discovery of new information. Chaotic systems can exhibit emergent behavior where complex pattern and structure arise from simple rules, generating new information. And chaotic environments can drive adaptation and evolution, leading to the creation of new information and knowledge. Hence, the concept of chaos is closely related to both entropy and information, and chaos is therefore the common point of entropy and information. And from this idea, the linkage between entropy and information was developed. The core idea of information theory is that the information value of a communicated message depends on the degree to which the content of the message is surprising. Okay, this is the point. Actually, the content of message. Entropy is related to the content of message. If a highly likely event occurs, the message carries very little information. On the other hand, if a highly unlikely event occurs, the message is much more informative. For instance, the knowledge that some particular number will not be the winning number of a lottery provides very little information, because any particular chosen number will almost certainly not win. However, knowledge that a particular number will win a lottery has high information value, because it communicates the occurrence of a very low probability event. Therefore, the information content, or the self information content, it is the concept of information content of a message, it is related with probability, and this concept of probability eventually brings the concept of entropy. Let us now define information in an objective way, because in order to develop the concept of entropy, we need to quantify information. That is how information can be quantified in an objective way, in a measurable way. That is the important point. In the previous discussion, we already discussed on different disciplines centered around the concept of information. That is, information is a highly contextualized concept, and information may be defined in different ways in the context of different broad disciplines and subjects. Now, we now discuss the information measure as defined by Shannon and show that Hartley's measure of information is a special case of Shannon's measure. For the sake of brevity, from now on, the description of the state of an object as a message, a term used by Shannon as well, while every message qualifies as an informational statement. The amount of information contained in a message varies from message to message. For example, suppose that a person from Delhi rings up the weather office in Kolkata around noon time and asks for weather information. In reply, he receives the message, "There is daylight here." Everyone knows that there is daylight in a place around 12 noon local time. Therefore, one may say that the information content of this message is zero, as it does not add to any new knowledge. On the other hand, if the message received is, "There is thunderstorm here with very heavy showers," then the informational content of the message is significant. But how significant is the informational content of this message? To answer this question, we need a measure of information. In order to develop the measure of information, let us consider another example. A person who is known to have breakfast regularly calls up his friend and says, "I had breakfast today." Now, the information content of this message is rather low, because the information conveyed by the message is the most expected status of the object in question. Actually, if he takes breakfast regularly, then the probability of this event is very high. Probability of occurrence is very high. If, on the other hand, the person tells his friend that he had not had his breakfast that day, then the information content is high, because the message conveys something that is less probable. That is, he had not breakfast, it is an event with very low probability. Hence, we have seen high probable event carries low information content, and in contrast, the low probable event carries high information content. This is the point. This is the basic axiom, fundamental axiom. Because the message conveys something that is less probable, thus, intuitively, we may relate the information content of a message to the probability of occurrence of the state conveyed by the message. Hence, we have seen the information content of a message is, however, related with the probability of occurrence of the event. If the probability is high, the information content is low, and if the probability is low, the information content is high. Hence, we may propose that the measure of information is inversely proportional to the probability of occurrence of the message. That is, let us see equation 1 where I will be inversely proportional to P or I proportional to 1 by P. Let us say this as equation 1 where I indicates information content of the message, P indicates probability of occurrence of the message. Let us suppose that the constant of proportionality is unity in equation 1. Then if p equal to 0, the value of I is infinity, and if p equal to 1, the value of I is unity. Actually, if p equal to 0, the value of I will be 1 by 0. It will tend to very large number or undefined number, and that is termed as infinity. And if p equal to 1, the value of I is unity. Now, if the probability p equal to 1, as in the case of the message, there is daylight here in the example considered above, you would like the value of I to be 0 rather than unity. To achieve this, hence we have arrived at a fallacy here, and to achieve this, we adopt a logarithmic expression that also serves as the constant of proportionality as in equation 2 below, that is I is equal to log of base 2 1 by p. So equation 1 was I proportional to 1 by p. If I equal to is written, then I equal to k by p, where k will be the constant of proportionality, but instead of that it is written as I equal to log base 2 1 by p. Now the value of log 1 is 0. Therefore, when p equal to 1, the value of I equal to 0, and when p equal to 0, I equal to infinity. Shannon, so p1 means high probable, so information content is 0, and p0 means low probable, information content is very high, that is infinity. Now Shannon chose the base of the logarithm as 2 as he was interested in binary digital systems. In binary systems, there are 2 bits or 2 binary digits, that is 0 and 1. That's why he chose the logarithmic base as 2. Sometimes the definition uses the base 10 on natural logarithm with base e. The quantity I is a dimensionless number, but by convention a unit is assigned to it. When the base is 2, the unit of information is called bit, and when the base is e, it is called net, and when the base is 10, it is called decit. The unit decit is also known as Hartley, named after RVL Hartley, who first proposed a measure of information. The use of base 2 is especially convenient when binary signals are used to convey a message. Now, equation 2 can be rewritten by using the laws of logarithm. We may recall that log of a by b equal to log a minus log b. Similarly, log 2 1 by p equal to log 1 minus log p equal to minus log p, as log 1 equal to 0. Therefore, I is equal to minus log p base 2 bits, equation 4. Now, equation 4 is the famous Shannon measure of information content of a message. As an example of application of the information measure that we have developed above, let us consider the following. If the probability of occurrence of a message is 1 by 4, then from equation 2 we obtain its information content of the message as I equal to log 2 1 by 1 by 4 equal to log 2 4 equal to 2 bits. Now Shannon's approach is source centric. Shannon was concerned with the probability with which a source may put out messages and proposed equation 4 as a measure of information. But interestingly, the equations 2 or 4 can be applied to recipient centered approach as well. If we replace the probability P with the recipient's expectation of information, then the same expression in equation 2 and 4 represent the informational value of a message from the recipient's point of view. In fact, we have used a recipient-centered reasoning in arriving at equation 2 without explicitly stating so. The fact that Shannon's information measure is applicable to both source-centric and recipient-centric studies makes it fundamental to information theory. Now, equation 2 or 4 is a measure for the information content of a single message. Now, let us consider a set of messages or a number of messages put out by a source that describes the state of an object, like, say, weather. As stated earlier, the number of states associated with an object may be finite or infinite. Accordingly, the set of messages put out by the source is finite or infinite. Without loss of generality, we consider a finite set of n messages for our further study. Let the n messages, that is m1, m2, mk up to mn, originate from the source with the probabilities p1, p2, pk, pn respectively. From the theory of probability, the probabilities of all possible outcomes must sum up to 1. We then have P1 plus P2 plus plus Pn equal to 1, because sum of all probability will be equal to 1. The information content of the kth message Mk is given by Ik equal to log base 2 1 by Pk. If the messages are statistically independent, the amount of information conveyed by two or more messages is the sum of information content of each message. Thus, for two statistically independent messages Mj and Mk, we have Ijk equal to Ij plus Ik log base 2 1 by Pj plus log base 2 1 by Pk. This is equation 7. Now the total information content of the source having a repository of n message is given by I source equal to log base 2 1 by p1 plus log 2 1 by p2 plus log 2 1 by pn equal to summation log base 2 1 by pk for 1 less than equal to k less than equal to n. If all the n messages are equally likely, then P1 equal to P2 equal to Pj equal to 1 by n. And the information content of any message Ij is given by Ij equal to log base 2 1 by 1 by n equal to log 2n, where 1 less than equal to j less than equal to n. In this case, the information content of all the messages is the same. Equation 9 is the one developed by Hartley and is a special case of Shannon's expression in equation 2 where p equal to 1 by n. There are other cases that are of interest. If n equal to 1, it means that there is only a single possible message with probability p equal to 1. In this case, no useful information is conveyed by the message and the information content of this message is 0. At the other extreme, as Pj tends to 0 and Ij tends to infinity, if n equal to 2, there are only two messages. If the probability of occurrence of one message is p, then by equation 5, the probability of the other message is 1 minus p. Applying equation 4, the information content of individual messages are minus log base 2p and minus log base 2 1 minus p bits respectively. Now, information entropy. Shannon's approach is source-centric. It is based on a simplistic view of the generally observed human communication process. In everyday life, it is the communicator source who decides what is to be said from all that could be said. In other words, source is the repository of messages and it is the source that decides what message is to be put out. Shannon's model assumes that the source acts independently without regard to prevailing situation or the condition and nature of the recipient. This is not true in human communication process. A human communicator subconsciously or consciously takes into the account the current situation and the capability and interest of the recipient before saying something. Here we discuss the average information content of a message in a sequence of messages put out by a source over a long period of time. The average information content per message is referred to as source entropy or information entropy, as is represented by the symbol H. As before, we consider a source with a repository of a finite set of n messages m1, m2 up to mn with probabilities p1, p2 up to pn. From this set of n messages, suppose that L messages have been gathered over a long period of time. If L is much larger than N, then the sequence of L messages will contain different messages from the set of N messages in the same proportion as their probability of occurrence. That is, M1 occurs P1 into L times, M2 occurs P2 into L times, and so on. The information content of individual messages is given by equation 2 or 4. Applying equation 2, the total information content of a sequence of L messages is I total equal to P1 L log 2 1 by P1 plus P2 L log 2 1 by P2 up to Pn L log 2 1 by Pn. This is equation 10. The average information content per message is thus given by H equal to I total by L. L is number of messages. That is, all else will be cancelled out here and it will give P1 log 2 1 by P1 plus P2 log 2 1 by P2 plus up to Pn log 2 1 by Pn. Equation 11 equal to summation pk log to 1 by pk for 1 less than equal to k less than equal to n. Applying equation 4, equation 12 may be rewritten as h equal to minus summation pk log to pk for 1 less than equal to k less than equal to n. Now equation 13, that is this equation 13, it is the famous Shannon's equation for information entropy, which is also called as source entropy. This is the equation for information entropy. Now, here, this equation can be interpreted as the entropy is the average information content per message of a source. We have seen that in the case of individual message, as p tends to 0, I tends to infinity, and as p tends to 1, I tends to 0. But in the case of information entropy, the contribution of an individual message to the average information content tends to 0 if its probability of occurrence is very low or very high. In other words, the quantity p log of 1 by p tends to 0 when p tends to 0 or 1. Thus, the average information content of both an extremely likely and extremely unlikely messages is 0. That is the point. This is a very interesting result. So, we have eventually seen the average information content of both an extremely likely and extremely unlikely, they are 0. Extremely likely messages has a very low information content and hence its contribution to entropy is very low. And on the other hand, extremely unlikely message hardly occurs. To be able to contribute significantly to the entropy, because extremely unlikely means almost zero probability. It may be noted that C equal to 0 at P equal to 0 and at P equal to 1. The maximum contribution occurs when P equal to 0.5. It is important to recognize the difference between the maximum contribution of a message to the entropy and the maximum value of entropy. The contribution of a message is maximized when its probability of occurrence is 0.5. This does not mean that the entropy is maximized. Entropy depends on the entire set of messages and hence on the probability of occurrence of all the messages. In fact, entropy is maximized when all messages occur with equal probability. We illustrate this fact in the following. Let us consider the case of only two messages in the message set with n equal to 2. Let P1 equal to P, then P2 equal to 1 minus P. The information entropy works out to be H equal to P log to 1 by P plus 1 minus P log to 1 by 1 minus P. If P equal to 0.5, then we have H equal to 1 bit per message. So this is the final result. For all other values of P, H has a value that is less than 1 bit per message. Similar results apply for cases where n greater than 2. The case of n equal to 2 has special significance in the context of binary digital transmission systems. If there are only two messages, they can be represented by 1 or 0 in the binary system. Message M1 is represented by say 1 and M2 by 0. Then if M1 were to be transmitted, a binary 1 is transmitted, and for M2 a binary 0. If the two messages are equally probable, then 1 and 0 occur with equal probability, as we know for P equal to 0.5, H equal to 1. This means that each bit in the binary system carries one bit of information. So this is the point. Each bit in the binary system, a single 1 or single 0, they carry one bit of information. This would not be the case if 1 and 0 do not occur with equal probability. This is the case if both occur with equal probability, obviously. Hence, this is the concept of information entropy. Thank you.